Welcome back, everyone. Today we're going to talk about proof by induction. Now, there's a chance that you might have seen this in some pre-calculus course before. I don't really understand why, but sometimes pre-calculus courses cover this. But if not, this will be new, and this is an exciting method that's used to prove statements that start for all n in the positive integers. Or sometimes slight variations of this, as we'll see. Ultimately, the fact that proof by induction works is a deep statement about the positive integers and their structure. So when I'm saying something about all n in the positive integers, I'm saying it about n equals 1, about n equals 2, about n equals 3, about n equals 4, and so on down the line. And so if I'm making a statement about all infinitely many positive integers, well, really I'm just saying it again about n equals 1, n equals 2, n equals 3, and so on and so forth. And so the special property of the positive integers here that I alluded to earlier is that they have this nice little structure laid out for them where I can put them in order. I have a beginning, that is, in this case, n equals 1, and then I can just leapfrog along, going from positive integer to positive integer to positive integer. Okay, so I start at the beginning, and I can just go along in this fashion. Note, this doesn't work for lots of other things we're interested in. So, for example, it would not work if I looked at all of the integers instead of just the positive integers. And the reason for that is that all integers don't have a beginning. There's no smallest integer to start at. The real numbers lack this ability to sort of go from one real number to the next one, right? If I start at, say, pi and say, hey, what's the next real number after pi? If you think about that for a bit, you'll realize that that's not really a question that has an answer. And so, because the positive integers have this very specific structure, it's possible to prove statements about all positive integers by thinking about these two things together. That is, by thinking about the beginning and thinking about the steps. So ultimately, what we're going to say here is that if I want to prove a statement about all positive integers, I can do that by proving the following two things. The first thing concerns the beginning. Namely, the first thing is I want to prove that it's true for n equals 1. We're going to call this the base case. And the second piece, which we're going to call the inductive step, has to do with this structure where we can go from one positive integer to the next, to the next, to the next. And that is, you have to prove that if the statement is true for a particular positive integer, then it's true for the next positive integer too. So, the first of these, the base case, is not so difficult to understand. If I'm going to prove that something's true for all positive integers, well, it had better be true for 1. So the fact that we have to check the base case, that kind of makes sense. Parsing out what the inductive step says takes a little bit longer. This is an if-then statement. And so the if part here is that we're supposing that this statement that we're trying to prove, whatever it is, remember I just said for all n in the positive integers something, and I haven't specified what the something is yet, that if it happens to be true for some particular positive integer, like say n equals 6, well then it's also true for the next one. So I'm not at all saying whether it is true for 6 or not, I'm just saying that if it is true for 6, then it's also true for 7. But likewise, that's true for every positive integer. So if it's true for 4, then it's true for 5. If it's true for 100, then it's true for 101, and so on. That's what the inductive step is asserting. Now, if you look at either of these pieces independently, they're almost worthless. So the first one, the base case, all it says by itself is that it's true for n equals 1, which I mean great, but it doesn't say anything at all about all of the remaining positive integers. If you look at the inductive step, that tells you that if this thing happens to be true for some particular integer, then it'll be true for the next one. But by itself, it doesn't tell you that it's true for any integers at all. The power is what happens when these two are taken together. So when I take these two pieces together, then as I said, in the base case, I learn that the thing is true for n equals 1. But now, because it's true for 1, if I also know the inductive step, then it's also true for 2, because 2 is 1 more than 1. Remember, what this inductive step says here is that if it's true for a particular integer, such as n equals 1, then it's true for the next one, such as n equals 2. But, again, if the inductive step is true, now that we've said it's true for 2, it's also true for 3, because 3 comes after 2. And, well, now it's true for 3, and so it's true for 4, because 4 comes after 3. And so on down the line. And eventually we're supposed to believe that this hits all positive integers. The best mental image here as to what's happening, I think, is to picture dominoes. And so you've seen these YouTube videos probably where someone stacks a bunch of dominoes in a row and then knocks them over. And the idea is, once I've sort of laid out this arrangement of dominoes, as soon as I tip this first domino, then all the dominoes will fall, because this one will knock into that one, this one will knock into that one, this one will knock into that one, and so on and so forth. And so what the inductive step does is it lines up all of the positive integers in a row like this, so that as soon as one of the dominoes falls, all the rest of the dominoes fall. And then once the inductive step has set up so that all the dominoes are arranged like this, so that once one of them falls, all of them fall, then the base case pushes over the first one. And then that gives you all of them. Now, I mentioned that this is ultimately a fairly deep statement about the structure of the positive integers. And by deep, what I actually mean here is that actually if you dig and dig and dig to try and find why this is true, what you'll eventually find is that the reason why proof by induction works is because it is literally an axiom for the positive integers. There are not ultimately that many axioms for the positive integers, as it would happen, but this is one of them. This is something so foundational to the structure of the positive integers that rather than it being something we prove, it is something we use to define the positive integers. So, all that out of the way, let's do several examples. So the first here is something that goes back to a story about Gauss. And namely, this concerns what happens when you add the first however many numbers. So if you add the first number, well, you get 1. If you add the first 2, you get 3. If you add the first 3, you get 6. If you add the first 4, then you get 10. And so the story goes that someday, when Gauss was in elementary school, the class was getting very unruly and the teacher was sick of it. And so the teacher just put on the board that the students had to all add by hand the numbers from 1 up to 100. And frustrating the teacher even further, Gauss immediately replied with the answer to this, which is that it is 5,050. And so how could you possibly guess this? Because I'm guessing Gauss probably did not actually add all 100 of these numbers by hand. And actually, if you look at these together, there's kind of a pattern here. And so you could actually guess the pattern. And the pattern is that if you add the first n positive integers, then you're always going to get n times n plus 1 over 2. And so you can check that at least against the handful of cases that I've written down so far. So for example, if n was 4, this would tell me I should get 4 times 5 over 2, which, as it would happen, is 10. Great. If you want to add the first 100 numbers by hand, you can check that you really do, in fact, get 5,050. And note, the reason why ultimately this is going to be an induction problem is that this is a statement about all positive integers. So what does the principle of mathematical induction say? It says that in order to prove this result by induction, I need to do two things. I need to prove the base case, and I need to prove the inductive step. So, first of all, as with all proof methods, you need to first tell your reader that what you're doing is induction. And so your informed reader, once they see the phrase, "we proceed by induction," they know they're expecting two things. They know they're expecting a base case, and they know they're expecting an inductive proof. The vast majority of the time, it is the inductive step that's hard to prove, and it's the base case that's easy to prove. That's not always the case, but in this instance, it certainly is. And so, like with our mutual inclusion proofs or our if and only if proofs, I recommend labeling each part of the proof. I don't have a symbol, I just write base case. And so what does the base case of this statement say? That's what this says when n is 1. Well, on the left-hand side, we get 1. On the right-hand side, we get 1 times 1 plus 1 over 2. And those are definitely equal, so that checks the base case. I want to stress again, all the base case here is saying is that if I sum all of the first 1 integers, then I happen to get 1 times 1 plus 1 over 2, which is very easy to check. Next, we have the inductive step. And you always have to prove the inductive step, but what is the inductive step supposed to say? It's supposed to say that if k is a positive integer, and this statement is true for k, then it's also true for k plus 1. Okay, so I have to put k plus 1 here in for k. Again, this is what the inductive step is always going to look like. It's going to say, if the statement is true for some particular positive integer, then it's true for the next one too. The strong tradition is that we use n in the original statement, and then also for the base case, but that we then use k and k plus 1 for the inductive step. Now, you might ask, why don't I just use n for the inductive step? And the answer is that you can't use n for the inductive step because you're still trying to prove a statement that has an n in it. And so, when you're here, you can't just start supposing things about n, as you will see. So here's where we are. We're trying to do a proof by induction, which means we have to prove the base case and prove the inductive step. We've proved the base case, and we have written down the inductive step. So, emphasis, we have to prove this thing. So I have written down this thing, but I don't know it's true yet. And so this is just like what happens when, as we've seen before, you write claim, colon, and then you follow that with a proof of the claim. I have to do that here. I have the inductive step, and then I need to have a mini proof of the inductive step inside the proof. So, what is that proof going to look like? Well, notice the inductive step is structured as an if-then statement. So it takes the form, if blah, 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 then more blah. And the structure of the inductive step is always an if-then statement. It's just an implication. And we know how to prove implications. Namely, we can use direct proof. So the inductive step, you are virtually always going to prove by direct proof. So what does the direct proof look like? Well, I'm going to suppose the if part here. If you're viewing this with a critical eye, you might well say, wait, didn't we just assume the thing that we're trying to prove? And probably having written many things on tests and homeworks and quizzes, you've probably had me lots of times tell you, you can't assume the thing you're trying to prove. But I want to note that what we've done here is we've not assumed the thing we're trying to prove, which is that for all integers n, this equality is true. Rather, we have assumed that for some particular positive integer, this statement is true. So this assumption is only for a particular positive integer. And that is why we have to use a k, or you don't have to use a k, but that's why we have to use a different letter than n. This note would not be something you would write up, but I'm writing it to you. So, we've supposed the if part of our inductive step is true. Now we have to get to the then part. Our then part involves this equation. And so, how do proofs work when you're trying to prove an equation? Well, as usual, we need to start by considering one of the two sides. Note, you definitely cannot write down the thing you're trying to prove as an equality. You have to start with one side, do some work, and get to the other. So in this case, I'm going to consider the left-hand side. Now I'm going to do a little magic to rewrite this. Namely, I'm going to rewrite this sum as follows. Now, this is exactly the same sum, because certainly the k was included in the ... So really, all that's happened is I've pulled one term out of this ... And so the consequence of this, if you want to be super particular, is that this ... is not the same as this ... But why have I done that? I've done that because now I can put parentheses around this. Now, again, that might not seem super impressive, but if you look at what we've assumed is we actually know what this thing is. So this is, by assumption, k times k plus 1 over 2. And this equality follows by what we call our inductive hypothesis, which is to say, by the if part of our inductive step. And all I mean by this is we literally started this whole problem by assuming exactly that this thing in parentheses was equal to this thing. So now that I have rewritten this way, I'm going to put this over a common denominator. So this is k squared plus 3k plus 2 over 2. And I can factor that, and this is going to factor as k plus 1 times k plus 2 over 2. And now, in case you've lost track of it, that was exactly the thing we wanted to prove. Namely, the then part of my inductive statement was that if I took this sum, I would get that. And so now I have this long string of equalities that starts on the left with that, and ends finally on the right with that. And now, by the principle of mathematical induction, we're done, because we've proven the base case and the inductive step. So again, why does this work? And it will take you a while to fully wrap your head around exactly what's happened here, and why we've really just proven something and not just sort of mooshed some symbols around. But again, what we did here was we showed the thing was true for 1, and if you follow this inductive step by plugging in k equals 1, where we know this thing is true, then this proof here that I wrote down proves that it's true for k equals 2. But then if I plug in k equals 2, this proof, just copied verbatim, would show me it was true for k equals 3. And then k equals 4, and k equals 5, and so on and so forth. And so, in total, the combination of these two pieces gives me that this is true for all the positive integers. Okay. I'm going to stop this video here. I'm going to do another video where I'm going to do endless examples of induction. Probably actually 2 videos of examples of induction, but we'll see. But what I'd encourage you to do is watch those videos, do some of the homework, think about this, practice, but later, once you have some experience, come back and watch this short video again, where I explain how the whole process works and why it works. And if you're still confused now, I hope that by then, all of these pieces will sort of come together for you, and you'll understand the whole of what we're doing in this section. Alright, I'm going to wrap up this video here. So I'll see you soon in the next video with more about induction.